We're going to focus on taking the word problem, and from the word problem, we want to be able to set up our constraints. We have another lab, 4.5, which we'll get to later. So 4.5 has 2 questions on it. We'll practice those later. We also have some additional exercises that I put at the bottom of the module here. So I want to start there. If you can click on the very last document in the module, it says 4.3 to 4.5 exercises. There are 2 practice problems on here that I'd like to go through, and then we'll jump onto the 4.5 lab and do those problems. All right. So these are just mixed applications from this section. Sometimes you'll be asked to minimize, some you'll be asked to maximize. Sometimes there'll be 2 unknowns, sometimes there'll be more. Sometimes your constraints will be all greater thans and less than, sometimes they'll be mixed. So it'll be a combination of all of those things. We want to read these problems and be able to set up the system, or set up the objective function and the constraints so that we can use a simplex method solver to solve. All right, step 1, always read the whole problem first. Pinocchio Crafts makes 2 types of wooden crafts, Jacob's ladder and locomotive engines. The manufacturer of these crafts requires both carpentry and finishing. So in order to make these, those are the 2 things we need to do, carpentry and finishing. Each Jacob's ladder requires 1 hour of finishing and half an hour of carpentry. Each locomotive engine requires 1 hour of finishing and 1 hour of carpentry. Pinocchio Crafts can obtain all the necessary raw materials, but only 120 finishing hours and 75 carpentry hours each week. Also, demand for Jacob's ladder is limited to at most 100 per week. If Pinocchio Crafts makes a profit of $3 on each Jacob's ladder and $5 on each locomotive engine, how many of each should be produced each week to maximize the profit, and what is the maximum profit? So remember, I always say, go to the last question, and that's where we want to start. So this last line has all of our good stuff, and particularly the second part. How many of each product should be produced each week to maximize the profit? So we're trying to figure out how many Jacob's ladders and how many, what's the other thing, locomotive engines we should have. We need to write out or assign a variable to each of those unknowns. So for our solution, we're going to start off by saying, let X represent the number of, what's the first thing? Jacob's ladders. I'll just call it JL. And let Y represent the number of locomotive engines, LE. Okay. So we need to assign variables to our 2 unknowns, and then we need to write out our objective function. Our objective here is to maximize the profit, and I'll write it in red since I have it underlined in red. We're told that each Jacob's ladder makes a profit of $3 and each locomotive engine makes a profit of $5. So our profit function would be P equals 3 times the number of Jacob's ladders, $3 for each one, plus 5 times the number of locomotive engines, 5Y. All right, that's where you should always start. Go to your question, figure out what you're trying to find, assign a variable for each of those unknowns, and figure out what your objective function is. Now for the fun part, what constraints do we have? Oops. We are told that we have constraints on our finishing hours and our carpentry hours. Remember, I said you guys can determine how you want to organize this data. Some of you may find it easy to just read through this paragraph and highlight the important information. Some of you may need to organize it in a table. We'll do both. So we're given information about, for our Jacob's ladder and for the locomotive engine, I'll make a little table. And we're given information about the finishing and carpentry for each. For the Jacob's ladder, it says we have 1 hour of finishing and half an hour of carpentry. Let's color code this. We'll let green represent the finishing. And so that was 1. And we'll let blue represent the carpentry. And that's 1/2 in this situation. All right, for the locomotive engine, I'll go back and highlight in a sentence in a minute. We have 1 hour of finishing and 1 hour of carpentry. So 1 and 1. And for my people who would rather not make this table, or you can't figure out how to make the table, again, you can just go through and kind of read the sentence. For finishing, it says 1 hour of finishing for the Jacob's ladder, 1 hour of finishing for the locomotive engine, and then also we have 120 finishing hours in total. For the carpentry, half an hour, 1 hour, and 75 hours in total. All right, so let's write out our constraints. First, for the finishing, we would have 1 times x plus 1 times y. Sorry, that's bothering me. I don't usually write the ones. 1x plus 1y would be x plus y. And we're told that we have only 120 hours of finishing. So should that be a greater than or equal to sign or less than or equal to? If we only have 120 hours, can we use more than 120 hours to finish this? No. It has to be less than or equal to that number of hours. Less than or equal to 120. For the carpentry, 1/2 x plus 1y, we have 75 hours. So you can use less than or equal to 75 here. All right. Now, there's something additional here. We read through all of this information. The first line just tells us, what 2 things we have. The second sentence gives us our information for the Jacob's ladder. The third sentence gives us our information for the locomotive engine. Then we're told the constraints we have on the numbers for each one, the finishing and the carpentry. There's something we're missing. We also have that the demand for the Jacob's ladder is limited to at most 100 per week. So we have an additional constraint here that's given. So Jacob's ladder, we're only going to sell at most 100 of those. So we need to make no more than 100 of those. X represents the number of Jacob's ladders. So that gives us the additional constraint that X has to be less than or equal to 100. So this is an example where we have an additional constraint thrown in. All right, and of course, we're making toys. We can't make negative toys, so X and Y both are greater than or equal to 0. Don't hesitate at all, you guys, if you find it a little tricky to set this up. This is literally being able to take a word problem like this and set up these constraints. It's like 70% of your test. Once you get this part, then all we have to do is enter it into the Simplex method solver. All right, to the solver we go. So we're going to type in that we're maximizing P equals 3x plus 5y, subject to x plus y is less than or equal to 120. 1/2 x plus y is less than or equal to 75. And x is less than or equal to 100. Did we miss anything? That's everything. All right, let's try it. So we are going to erase everything that we had before. Now we're maximizing. Maximize P equal to 3x plus 5y, subject to I'm sorry, just want to make a little space there. You do not have to put these spaces in. I'm just doing it so that we can see it a little bit more clearly while we're typing. All right, the first one was x plus y was less than or equal to 120. The next one is 1/2 x. Now I'm going to put that in parentheses, the 1/2. So parentheses 1 divided by 2, close parentheses, x plus y is less than or equal to 75. And then our last constraint was that x had to be less than or equal to 100. All right. Always double check, make sure everything is typed in like it's supposed to be. Your inequalities are going the right way. Your variables are correct. No typos. And then from here, I think everything looks fine. Hit solve. And there's our answer. Now I just want to show, because I did not type in that x had to be greater than 0, y had to be greater than 0 into the solver. Solver kind of already knows that. If I type it in though, I just want to show you that we still get the same answer. So x is greater than or equal to 0, y is greater than or equal to 0. So if I add those and hit solve, I don't know if you can tell I'm tapping it, I still get the same answer. I'm going to erase it and then hit solve again, just so you can see that it's the same answer coming up. All right, so that's our optimal solution. P is 420, x is 90, y is 30. Let's go write that up. Oh no, I think I erased everything. Oh, okay, that was a close one. All right. So our solution here P is 420, x is 90, y is 30, and then you need to write out in words what this means. So we'll say the maximum profit is $430 or $20 when 90, what was 90? The Jacob's ladders, 90s Jacob's ladders and 30 locomotive engines are produced and sold. And that's it. Hopefully you're starting to feel like this is very repetitive. Same thing over and over. You get it. If so, good. Because it's more of this that's just going to keep coming. All right, on to exercise 2. Let's see, what are we doing in exercise 2? A company manufactures desks and computer tables at plants in Texas and Louisiana. At the Texas plant, production costs are $12 for each desk and $20 for each computer table, and the plant can produce at most 120 units per day. At the Louisiana plant, costs are $14 for each desk and $19 for each computer table, and the plant can produce at most 150 units per day. The company gets a rush order of 130 desks and 130 computer tables at a time when the Texas plant is further limited by the fact that the number of computer tables it produces must be at least 10 more than the number of desks. So there's a lot going on here, a lot of information we're going to have to organize. The question is, how should production be scheduled at each location in order to fill the order at minimum cost, and what is the minimum cost? All right. So we know we're trying to minimize the cost. Cool. What are we producing and making here? What are our unknowns? And how many do we have? So we know that we're making desk and computer tables. In a desk, a computer table. Okay, desk and computer tables. We're making two of those two things, but we're also making them at two different places. So there are desks that are being produced in Texas for $12, and then there are desks that are being produced in Louisiana for $14. Okay, and then there are computer tables being produced at each place also. So we need a variable for each product at each location. So there are 4 unknowns altogether here. We'll do X, Y, Z, and W. Let X represent the number of desks at the Texas plant. And we can let Y represent the number of computer tables. I'll just put tables at the Texas plant. And then we also need the number of desks and tables at the Louisiana plant. Okay, so X, Y, let Z represent the desk at the Louisiana plant. And let W represent the tables at the Louisiana plant. All right, and then we have to be very careful about how we're organizing our information here. Essentially, we're trying to make 130 desks and 130 tables, at least that amount, right? Because we got a rush order for that. And then we have a bunch of different constraints on things. And then we also are trying to minimize our production costs. So we have our unknowns here. Next step is we want to write out our objective function. We want to minimize C equal to what? So in here, we're told that it costs $12 for each desk and $20 for each computer table at the Texas plant. So for Texas, that would be 12X plus 20Y for our cost. And then for the Louisiana plant, the costs are $14 and $19. So that would be plus 14Z and then plus 19W. So we have 4 unknowns here. I think we have it all highlighted correctly. 12 times the X, the number of desks from Texas, 20 times Y, the number of tables from Texas, 14 times Z, the number of desks from Louisiana, and 19 times W, the number of tables from Louisiana. All right, now that we have that information, okay, we also have that each plant can produce at most 20 units per day. Let's go through all of the different constraints that we have. Well, first, and I'm going to highlight them all, and then we'll put together the information. I hope I don't run out of colors. All right, we'll go with green first. It says that the the Texas plant can produce at most 120 units per day, and the Louisiana plant can produce at most 150 units per day. So let's start with those two. For the Texas plant, sorry, we're down here to our constraints. So in green, we have in Texas, they can produce 120 units per day. Units mean either a desk or a computer table. When we put those things together from the Texas plant, should be no more than, or at most, 120. So which of our variables represent things coming from the Texas plant? That would be X and Y. So when we add X and Y together, the number of units produced in the Texas plant, this has to be less than or equal to 120. Because we're told we can produce at most 120 units from that plant each day. purple. From the Louisiana plant, that's Z and W come from the Louisiana plant. Z plus W can be at most 150. So that has to be less than or equal to 150. All right. Going down to our next line after what's highlighted there in the purple, it says the company gets a rush order of 130 desks and 130 tables. Okay. Uh-oh. What color? What more? Name more colors. All right, let's go. Yellow, we need 130 desks. And can't highlight in black. That's boring. Oh, look at the pink. Okay, let's go with orange. 130 computers. All right, so we need 130 desks and 130 computers. From our variables, which variables represent desk? If you look at what we have up there, X is the number of desks from Texas, Z is the number of desks from Louisiana. We want to put those things together. X plus Z has to be, we need at least 130 of them. It doesn't say at least or at most, but we have an order of 130. We need to make 130 because that's what the order is for. We can also make more than that. So it can be greater than or equal to 130. Similarly, for the computer tables, we'll have Y plus W has to be greater than or equal to 130. All right. And last thing, did I use blue? Oh, I haven't used blue. Okay. Last thing, we're told that the Texas plant is further limited by the fact that the number of computer tables, this is in Texas, the number of computer tables it produces must be at least 10 more than the number of desks. All right, so in Texas, the number of computer tables is Y. That has to be at least 10 more than the number of desks. So Y has to be greater than or equal to X plus 10. That would be 10 more than the number of desks. This one was good. Your project that you're going to have for this chapter is kind of similar to this also. All right, I'm going to pause. Look, we got the whole rainbow in colors for this one. So there's a lot going on here. First, we had to recognize that we were making desks and tables at two different places. So we had to have a variable to represent each desk and each table at each different plant. So that gave us 4 unknowns. We were able to set up our objective function. We were given lots of different constraints. We were constrained on the number of units we can produce at each plant, 120 in Texas, 150 in Louisiana. We were constrained on how many desk and computer tables we need. We needed 130 of each. And then we were constrained on, in Texas, there had to be at least 10 more desks than, or sorry, the number of computer tables had to be at least 10 more than the number of desks. All right, so we got all of that written down, lots of stuff here. Hold on, one of these is bothering me in color. Never mind, I've run out of good colors. So now that we have this, we're going to put it into the simplex method solver. A couple things I want to point out here. For several of the problems that we did in the last class, and even the last one also, we had 2 unknowns. And in the last class, someone asked, well, if I wanted to solve this graphically, could I? When you have 2 unknowns, yeah, you could solve it graphically if you wanted to. For something like this, though, where you have 4 unknowns, and then we have these 1, 2, 3, 4, 5 different constraints, and all of these different variables, X, Y, Z, and W, you wouldn't be able to graph this. This is one where you would need to use the simplex method to solve. All right, let's type all this stuff in. I'm gonna have to go back and forth. Actually, I am going to sneak and use my phone to take a picture so I don't forget all of these things. All right. Here we go. All righty. Now let's go on to the simplex method solver. Erase everything from the last problem. Our new objective is we're trying to minimize our cost. Minimize C equal to, and we have lots of variables, 12x plus 20y plus 14z and 19w. Subject to x plus, the first constraint was x plus y is less than or equal to 120. Less than or equal to 120. That's the constraint on the Texas units. For the constraint for the Louisiana units, we have z plus w is less than or equal to 150. Then for the number of units we need 120 desks, 130 desks and 130, what was the other thing? Computer tables. So we had x plus z for the desk. Is greater than or equal to 130. Again, we use greater than or equal to here because we have an order for 130 of them, but we can make more. We just have to at least meet the order. So it could be greater than 130 or equal to 130. Can't be less than that. Similarly, y plus w has to be greater than or equal to 130. Okay, and then the last one, well, actually, let me go back. So for the last one, this is correct the way that I have it written. Y is greater than or equal to x plus 10. You can keep it that way if you want to. But for all of the other constraints, we have it written where all of our variables are on one side and we have a constant on the other side. If you wanted to write this last one that way, you could also write this as y minus x is less than or equal to 10. I'm sorry, greater than or equal to 10. So you can write it either one of these ways. All right, I'll just keep it the way that we had it originally, which was y is greater than or equal to x plus 10. All right, I think that's all the stuff. I'm just gonna go back through, and you should too. Take your time, make sure all of your variables are typed in correctly. There are no typos. Since we have mixed constraints here, some greater than or less than, some greater than or equal to, some less than or equal to, you wanna double check that information. Everything looks good here. X plus y less than or equal to 120. Z plus w less than or equal to 150. Because that's the constraints that we have from each plant on the number of units we can produce. We need 130 of desk and tables, and y is at least 10 more than x. All right, I believe us here. Once you have everything in, then you hit solve. All right, and we get this optimal solution. 4,077, x is 111, y is 9, z is 19, w is 121. Okay, so we're going to take that optimal solution, write it on our paper, and then write out in words what this means. So last step here, our solution. We have C equals 4,077, X is 111, Y is 9, Z is 19, W is 121. And what does this mean? The minimum cost is $4,077 when, what is X? X represents the desk from the Texas plant. Y represents the tables from the Texas plant. So we can say when 111 desks and 9 computer tables are made in Texas, and 19 desks and 121 computer tables are made in Louisiana. All right, I like this problem a lot. Again, for your project that you're gonna have, which will be due after your test, it'll be a linear programming problem like this, kind of similar, where you have 2 different plants and 2 different products. So you end up with 4 unknowns altogether. Now this problem was a lot more involved. It might have been a little bit more challenging to set something like this up on your own. So this is a really good example to go through. All right. Now we can go over to our lab. Oh no, I'm on the wrong thing. We're on lab 4.5. We only have a few more minutes left. We won't be able to finish the whole thing. Again, there's a link for the Simplex method solver at the top of the lab. You can use it again. I will read through problem number 1 and kind of help us get set up with this one. And then I'll leave you to do the Simplex method part, and then also to do the second problem that's on here. So you can finish this up on your own, get some practice in. All right, so what's going on here? Rachel's job allows her to sell merchandise in cities A, B, and C. From her office, it is 95 miles to city A, 35 miles to city B, and 72 miles to city C. At each city, she earns $950, $554, and $780 respectively. The cost of travel to each city is $65, $62, and $90 respectively. If she can travel up to 2,000 miles and her expense account allows her to spend $250 on her trips, how many trips should she make to minimize her sales? Okay. So how many trips should she make to, I'm sorry, I was about to say, why would she want to minimize her sales? I read it wrong. So maximize her sales, which makes much more sense. If you're selling, you want to sell as much as possible. All right. So our goal here is to maximize our sales, and we're doing this by traveling to each of these cities. And we're trying to figure out how many trips she should make to each city. How many cities do we have? We have 3, A, B, and C. Now, this is a case where instead of using X and Y and Z like we've usually been using, it might be easier to just use A, B, and C. We already have variables there. So let A represent the number of trips. It says complete sentence. So let A be the number of trips to city A. B the number of trips to city B. And C, let that be the number of trips to city C. Oh, you can leave that red. Then the objective function. Our objective is to maximize our sales. The second sentence where it says, at each city she earns $950, $540, and $780. This is representing how much she sells. So we're trying to maximize the sales for each trip. Okay, so that's that's the information we need for the objective function. We want to maximize C equal to, we would have $950 for each trip she makes to city. Look at me, I call it city X. It would be city A plus $554 for each trip to city B plus $780 for each trip to city C. All right, now our constraints here. We are told that she can travel only 2,000 miles. That's one constraint. And her expense account only allows her to spend $2,500. So we have constraints on how far she can travel altogether and then how much she can spend. And we're given information about each of those things. So for the distances, we're told that cities A, B, and C are 95 miles, 30 miles, and 72 miles. That gives us the constraint that 95A plus 35B plus 72C. When we put all of that together, we can travel up to 2,000 miles. So that has to be less than or equal to 2,000. And for the cost to travel to each city is $65, $62, and $90 respectively. So that's $65 for each trip to city A, $62 for each trip to city B, and $90 for each trip to city C. And that has to be less than or equal to $2,500 because that's the most money that she has to spend. I think we took care of everything that's given there. And of course, X, Y, and Z, I'm sorry, A, B, and C represent the number of trips that we're taking. They can't be negative. So A, B, and C all have to be greater than or equal to 0. All right. I think we got everything. That's it. So from here, you would go to the Simplex method solver, write out your optimal solution, and then write what that solution means in the complete sentence. Now, I'm going to stop here. There is one more problem on the lab also that you'll have to set up about iPhones. What's an e-phones, my bad. We don't want any copyright infringement. An e-phone, an e-pad, and an e-laptop. Okay, so you're trying to optimize the number of hours that you should schedule to make each of these different technologies at minimum cost, okay?